Hello. We're going to be talking about combustion. So, of course, it is very appropriate to light some matches. These are those green phosphorus tips. They're kind of cool. And let's light this soy wax candle. So all of these are examples of combustion. We were combusting that phosphorus. I don't know if this is going to take. Come on, get in there. No, it didn't take. We were combusting the phosphorus on the tip here. And then it began to burn the wood, which is cellulose. And now I'm trying to get it to burn this wax here. Get it in there faster. Okay, got the wick up. There we go. Okay. All right. So in these combustion processes, we have carbon-based compounds that we're looking at. They don't always have to be carbon-based, but that's what I'm going to be talking about. We could, of course, have the phosphorus like we have in the matches, or we could have hydrogen. But carbon compounds burn really well. They work very well as fuels. And so what does this mean if we have a fuel? Why do we choose to burn wax? Why do we choose to burn gasoline or natural gas, which is methane? And the reason is we get energy out that we can then use. And energy mostly in the form of heat. There's also some entropy there with the explosion, essentially. If you think of a piston inside of a car and the outward motion of those molecules inside there as the vapor of the gasoline combusts, and there's this dispersion of energy, that is entropy, an increase in entropy. But a lot of it is the heat that we get out. So I wanted to talk about combustion reactions, to talk about the energy changes, but also to start out just talking about balancing them. So I have a method that, I don't know, maybe it appears in textbooks. I have never seen it, but it's probably out there. I don't think I made it up. But there's a way to balance combustion reactions that works pretty well. It's pretty reliable. So, let's talk about combustion reactions. All right. And as I said, we'll focus on carbon-based compounds. So why don't we start out and look at methane. Methane is the main component of an natural gas. Natural gas also has some ethane in it, but we'll focus on talking about methane right here. Methane is CH4. And so, with combustion reactions, our fuel, our carbon-based fuel, is reacting with oxygen. This is actually one of the earliest chemical reactions that was studied back in the 1700s by Antoine Lavoisier. And I think because it's just easy to burn stuff, right? So he was looking at different kind of compounds, reacting them with oxygen and studying them. So what do we get when we combust a carbon-based compound like this simplest hydrocarbon here, methane? Well, if there's a lot of oxygen, then we're going to get carbon dioxide. And water. So these are on the gas phase. I'm not going to put gas there just to simplify it. We can just focus on the molecules that are here. So if this is our combustion reaction, it's not balanced yet. I wanted to show you this technique I was alluding to earlier, which is the first thing that I do is I look at the fuel itself. And I look and I see how many hydrogens are there. And then the first thing I do is I then, based on that number, I balance the water molecules. So for example here, we see there's H4. And so, to balance the hydrogens in water, we will need a 2. Ooh. Actually, we will need ink first. And then we will need a 2. Okay. So put our 2. Okay. So that's my tip. Where to start. Balance the waters first. Okay, then we see that hydrogens are balanced. And then what I'm going to do is skip over the oxygen, because we're going to do that last. And I'm going to double check that the CO2, which is the only product that has carbon, has enough carbons to match the carbons over on the fuel. Now in this case, methane, being the simplest hydrocarbon, only has 1. So we are all good. And then, last but not least, we balance the oxygen. This one is best to save for last because it's elemental oxygen. And so we can put whatever stoichiometric coefficient we need in front of it to finish off the balancing process. So if we look here, we see we've got 2 oxygens here with the water, 2 oxygens with this one CO2 molecule, so a total of 4. And because O2 has 2 oxygens per molecule, we will need 2. Oh, come on. I think I need a new nib. This part of the calligraphy pen that I dip into the ink, it's called a nib, N-I-B. And I think when they get old, they don't hold the ink as well. Anyway, there we go. Nice and balanced. So, once again, just to recap, when you're balancing combustion reactions, balance the water first based on how many hydrogens you need to balance with the hydrogens on the fuel. Then, balance the CO2 based on how many carbons you need, again based on the fuel. And then last, balance the oxygen. Okay. So here's our combustion reaction, methane. And I wanted to point out that the enthalpy change for burning methane, so this is essentially how much heat we're getting out for this chemical reaction. So I'll call it the enthalpy for this reaction. Combustion reactions are always exothermic. Okay, for these kind of carbon-based compounds, just like our candle over here burning the wax. Wax is a big carbon-based compound, and it's letting out heat as well. So this is going to be exothermic, losing heat from the system into the surroundings. So we expect there to be a negative sign here. And for methane, it is minus 890.2. And this is kilojoules per mole. Okay. So I wanted to bring up something that's talked about a lot, right? And that is carbon emissions. And that's discussed a lot with fuels in the context of how much fuel you're burning and then how much CO2 is emitted. And so here, if we have 1 mole of our methane, and if we burn 1 mole of that methane, we get how many moles of CO2? We look back at the stoichiometry, it's 1 to 1. So that's a good, nice, easy problem to start with, right? For 1 mole of CH4 burned, we get 1 mole CO2 emitted. So that's for natural gas. What about another kind of gas? Let's look at, as a comparison, let's look at propane. That's used a lot, right? Our propane tanks, very common fuel. Propane, this prefix pro means 3. So this is 3 carbons. And in propane, there are 8 hydrogens. And we could go through the same process. I don't we do it? We'll do it faster this time. Just check how we would balance this combustion reaction. H2O. Okay. So let's look at this. If we use the technique, we look at propane, and there are 8 hydrogens. So we balance them out by putting a 4. Now we look at C3, and so we need a 3 to balance our carbons. And then we look over the oxygens. Here there's 4. Here 3 times 2 is 6. Total of 10 over here. So for O2, we need a 5. Okay. So now for carbon emissions, we can again look at the stoichiometry. And now for propane, if we look at it from the same point of view, just looking at moles, for 1 mole of our propane, we now see that there is a 1:3 ratio. So now there are 3 moles of carbon dioxide emitted. So I wanted to bring this up because there's a lot of discussion about, well, carbon emissions are seen to be bad. More CO2 in the atmosphere can affect temperatures on Earth. It can also affect acidity levels in the oceans. But looking at it from just this point of view of burning 1 mole of this fuel gives 1 mole of CO2. 1 mole of this fuel gives this much CO2, which is 3 times as much as that. And from this point of view, it looks like natural gas is better, right? But it is very relevant to bring in enthalpy, right? How much energy do we get out for that 1 mole of the methane? And in this case, it was minus 890.2 kilojoules per mole. Well, what is it for propane? So now we've talked about just the relative amounts of carbon emissions, but in terms of the energy, what is it for propane? What do you think? Do you think it's going to be more or less than methane? Let's take a look. Okay. It is, drum roll please, 2, 1, 9.9. Yes, that's right. 2,219.9 kilojoules per mole. Okay. So we do get a good amount of energy out of this. Now, it's not 3 times as much as that, okay? But it is definitely more than twice as much as for the methane. Okay. So there are a lot of, ooh, that was pretty. There are a lot of different considerations with the different gases, also the sources that they come from, and Their costs, of course, affect some things, and how they are transported is a whole nother issue. So there's a lot to think about. And also, whether or not they are renewable, right? So, in the case of both of these fuels, for the most part, these two predominantly the sources that we get of methane and propane are non-renewable. So these are fossil fuels, and they're from sources within the earth that aren't regenerated. They're already there, and we're just extracting them. But there are some lovely carbon-based fuels that are renewable. So before we go, I just wanted to highlight what those are. Okay. I'll just give you a couple of my favorite, and these are renewable fuels. Now, notice that renewable fuels, this is different from another renewable energy source, such as solar or wind or geothermal. I am specifically talking about fuels, which means chemical compounds that you can burn, that you can react with oxygen. So in terms of renewable, we have ethanol, and ethanol you can get by growing plants and fermenting them, just like we do with ethanol that we drink. Same kind of idea there. And ethanol burns quite efficiently and has low carbon emissions. Also, there's biodiesel. So biodiesel comes from fats that are within growing plants, which usually it's in the seed part of it, where there are those triglyceride fats. This is supposed to be an E, by the way. B, biodiesel, not ow. And my very, very, very favorite is hydrogen. And one of the many reasons why hydrogen is my favorite renewable fuel is that the combustion reaction with hydrogen looks like this. Hydrogen, there's our fuel. Oxygen, we combust it with. And ta-da, here's our product. Oh, I wrote the 2 there. That's okay. Water. That's it. Then we need a 2 here. The product is water. Because there's no carbon in the fuel, there will be no carbon emissions. So, quite a lovely combustion reaction here. And hydrogen fuel can be created by the water splitting reaction, taking water and essentially doing the reverse of this, which is really the trick and is the thing that a lot of people are studying, of how to do that efficiently using catalysts. But I tell you, once we have a renewable source of hydrogen that can be made efficiently, very lovely. All right. Well, there's a little bit about combustion reactions, and I really combined a lot of concepts here. I brought in a little bit of enthalpy and a little bit of balancing chemical equations, and talked a little bit about stoichiometry. And also brought in one of my favorite topics of renewable versus non-renewable fuels. I should say non-renewable versus renewable. And giving a little shout out to my hydrogen fuel. Thank you, hydrogen. All right. Well, thank you so much. It's so good to be back, and I have loved all the messages from you. So keep them coming, and I will keep the videos coming, and we shall continue our chemistry journey together. I will see you next time.